So the task is the following. For example, this can appear, this kind of question, in your practical work. We have a tank of high pressure and then flow from this tank using the nozzle, the subsonic and supersonic nozzle. And we are measuring some flow parameters in the nozzle. And the question will be how to calculate another flow properties like a Mach number, for example, in any point where we measure the pressure. So I will have the following drawing. It will be some axis of the symmetry. Okay, somewhere I have a tank. I will make it very small because we don't need to show a big tank. And then it was a subsonic part of the nozzle and some supersonic part of the nozzle. Now for us is not very important what is the geometry, because independently on geometry, if we measure the flow, we can calculate the flow properties. Okay. Somewhere in the tank we have high pressure, which is, let's assume it's P0, stagnation pressure, because inside the tank we have a very, very small velocity, approximately equal to 0. And we have some pressure sensors. Where we can put the pressure sensors? Quite obvious that these pressure sensors will be on the wall. I will make some space for the sensors here. And for example, I will put somewhere here, pressure sensor will be my P1 measured. Okay, let's assume some value. Okay, 0.6 bar. Then I have another point of the pressure measurement is, for example, P2. Let's have some, since our flow is accelerating, we will have some reduced value of pressure. For example, 0.1 bar. And somewhere close to the exit, we will have another value of the pressure, let's say equal to the ambient pressure, P3 is equal to 1 bar. So what we know from the theory of the shock waves, that sudden rise of pressure from point 2, point 3, from point 2 we have 0.1 bar, and from point 3 we have 0, 1 and 1, so it's 10 times pressure growth, and probably between these 2 points we have a normal shock wave. How we determine? Quite easily that if we have a smooth geometry, we cannot have a sudden rise of pressure without anything. If we have a sudden rise of pressure, it means that our potential energy of the flow increased, and means that the kinetic energy suddenly decreased, and it can happen only through the shock wave. In our case, it's a normal shock wave. So I will make it more visible. Pressure 1 sensor, pressure 2 sensor, pressure 3 sensor. Static pressure flow measurement, where the flow velocity is perpendicular to the tube. Right? So we measure just the static value. Okay, I'm not showing anything about the Mach number. We have to determine actually. So let's think what we can calculate from here. We can calculate, for example, in this cross section, Mach number. It will be our Mach number 1. We will calculate from this cross section Mach number 2, and we will calculate from this cross section Mach number 3. Okay. So these values of Mach number we are interested to know, to calculate from a theoretical point of view. What are the values of the velocities? Once we know the Mach number and we can know the temperature, we also can calculate the velocity values in meters per second. Okay, let's proceed with the Mach number. first of all, we need to agree about the flow model. What is the flow model acceptable for such kind of the flow process? When we look the nozzle, usually we assume that the flow in the nozzle is isentropic. So we do not have a heat transfer and we do not have a boundary layer. Actually, we in real flow have a boundary layer and the heat transfer, but in the simplified case like our, we will assume that flow is isentropic. So no heat transfer, no boundary layer. And all this isentropic flow is happening over here inside the volume until we meet the shock wave. Once we meet a shock wave, flow is changing completely, and as you know, the shock wave by itself is not isentropic. So I will make a shock wave schematic. The actual position of the shock wave we do not know yet because we did not study this part of the book yet, but very soon you will be capable to obtain what is the actual position of the shock wave inside the nozzle. For this, we need to know theory of the flow in the nozzle. It will be a bit later in future. Right now, what we can do, we can just calculate Mach number independently on the nozzle geometry and independently on the shock wave position between these 2 points. So, what I have, isentropic flow everywhere here, isentropic here, isentropic, and here, isentropic. Transition of the flow from one section to another through the shock wave is not isentropic, non-isentropic flow. So we will use these models here. If we see that we have isentropic flow in these first 3 regions, we understand that automatically P0, stagnation pressure, would be constant for all these flow regions. So for this region, and for this region, and for this region as well, would be constant value. Once we define P0, we can use it for any region. Okay, and for the region of transition, through the shock wave, flow will not be isentropic, but we know using the second law of thermodynamics how to calculate the pressure drop, stagnation pressure drop. So we know that P0 at 0.3 divided by P0 at 0.2 is a function of Mach number. This function of Mach number exists in the book and also is presented inside Appendix B. Here, as a practical example, I will just use Appendix B, which is an exactly representation of the formulas from the book. Okay, so 3 volumes with isentropic flow, 1 transition in a non-isentropic flow. And we have what we can measure in the real case. We can measure only the pressure. We cannot measure directly the Mach number, right? It's very hard to measure the flow velocity, temperature, especially if the flow is hot inside the nozzle. So difficult to measure other parameters than the pressure. So based on this pressure, we will try to calculate other flow properties, at least the Mach number and stagnation pressure. Okay, let's start from the normal shock wave theory. This is our normal shock wave. And based on normal shock wave theory, we can see the pressure drop. As we know, on the normal shock wave, we have, I will just skip a bit, move down. From the normal shock wave theory, we have the following formula, that pressure ratio before and after the shock wave, actually after and before the shock wave, in our case it will be P3 divided by P2, is a function of the Mach number before the shock wave, Mach number 2. This formula, it has a number in the book, 865. So I will not use directly formula 865. Instead of it, I will just use the table inside Appendix B. So I will calculate my ratio of pressures. So this pressure 3 divided by pressure 2, since I know the values, it's 1 divided by 0.1 would be equal to 10. So we have 10 times pressurized. And this is some function of Mach number 2. And from here, I will see that my Mach number 2 from this formula would be equal to 295. So this is my M2. And since we are already determined the Mach number before the shock wave, we have another relation inside the theory of normal shock wave, which saying to us what is the relation between Mach number before and after the shock wave. We know that Mach number after the shock wave is a function of Mach number before the shock wave and the adiabatic constant, which is constant in our case. And from here, since we know the function, how it looks like, and we know the value of M2, we can calculate that M3. And in our case, M3 will be 0.48. Okay. This is the Mach number after the shock wave. Just using this relation here, or Appendix B, I can calculate the Mach number after the shock wave. We cannot say anything about stagnation pressure yet, because we must determine stagnation pressure before the shock wave to make relation between stagnation pressure before and after the shock wave. And to make this, I will just write for you two relations. One relation will be about the, since the flow is isentropic, I will make relation between pressure 1 and stagnation pressure P0. And another relation I will make between pressure 2 and stagnation pressure. The isentropic relations, again, they are known from the chapter 8. Let's write the following. And they are also known from the Appendix A. So you can use our formula or Appendix A. We can write from the formula that P0, which is constant in the first and second measurement of pressure, divided by pressure 1, is the sum function of Mach number at point 1. And the same way we can write for the pressure 2 that P0 divided by pressure 2 is some function of Mach number 2. Okay. From here we can calculate from the second formula. I will calculate what is my stagnation pressure, because we already know what is Mach 2, right? 295. We already know what is P2, which is 0.1 bar. And we know the function from the book, or we use Appendix A to substitute function by the table. So from here I will write that my P0 is equal to function of Mach number 2 from the book, or from Appendix A, multiplied by P2. Okay, this is it. Now I can calculate. I go to Appendix A, and I will see that this function from Appendix A, as I know M2 already, would be equal to approximately 34. And my P2 defined by the task, by the initial conditions for this task, is 0.1. So my stagnation pressure will be equal to P0 equal to 3.4 bar. Okay, 3.4 bar. This stagnation pressure, again, I repeat, is the same for the region 1, for the region 2, and for the region 3. It's the same as isentropic flow because we do not have inside this flow any heat transfer, we neglect the boundary layer, and we do not have a shock wave. So flow is isentropic. Now, when I calculated my stagnation pressure for these three regions, I can go back and calculate the Mach number. I can calculate the Mach number. For this, I will need my pressure to know the pressure 1 at point 1. Okay, and I will write that same relation which I had from the appendix A. I will write for already using the numbers. So let's write at P0 3.4. My measured pressure at point 1 is 0.6. Okay, and this is equal to the function of Mach number 1. I know the left side, I know the function on the right side, only a one unknown is Mach number. And from here, using appendix A, I will see how much is this ratio. So it's actually, the ratio is 566 or 5.7, approximately 5.7 here. And from here, the function of M1 is equal to 5.7. I like approximate numbers, you know, it's very nice to have short numbers. For this just demonstration case. And from here, Mach number 1 from this function would be equal, let me see, is 1.8. Mach number is 1.8. So we defined by the last operation, which is the Mach number at point 1 here. So now we know P0 3.4. This is Mach number 1.8. This Mach number is 295, and this Mach number was 0.48 at point 3. So we know the Mach number everywhere. Now, since we know these values, we can also go to calculate the temperature. To know the temperature, we need some reference temperature at some point, somewhere. It's not so much important where we will define the temperature, because we can calculate from one point to another, and for us is absolutely irrelevant where this point is placed. We just need to make a reference in our schematic. Okay. So I think it would be nice if we put the stagnation temperature somewhere here in the tank. For example, we know that T0, it's very easy. Put the thermocouple inside the tank, the flow is not moving, so you measure exactly the stagnation temperature. And let's see, it will be a bit elevated with respect to the ambient temperature, and it will be, okay, let's assume 400 Kelvin. 400 Kelvin. And I will try to calculate other temperatures we have in the system. So this stagnation temperature, as you know, this also keeps the constant for all regions inside the isentropic flow. So we have 400 Kelvin stagnation in point 1 and in point 2 as well. And then we will make transition to point 3, from point 3 to pressure 3, or from region 3 to region 4. Okay, 4 would be here. And we will calculate the temperature here at the exit of the nozzle, where pressure is again 1 bar. To calculate inside point 1 and point 2, I will use isentropic relations from the book. Just a moment. Now I will open these isentropic relations just to give you an idea which formula I am using, the number, and then we will calculate, not using the formula, but using the equivalent Appendix A from the book. Okay, it's this one. General formula is the following. Temperature stagnation divided by temperature at any arbitrary point would be equal to 1 plus gamma minus 1 divided by 2 multiplied by Mach number and square. This is formula 840. Or inside Appendix A also we have the same relation. So for my case 1, I will use just subscript 1, temperature 1 and Mach number 1. And I will be capable to calculate because my Mach 1 is known. We already calculated before. And temperature 0 is given, so the only unknown here is temperature 1. I will use all this right part of the equation just as a function of Mach number 1. Okay, just to simplify, to make more compact written part. So in my case, let's see, our T1 would be equal to T0 divided by this function of Mach number 1 from equation 840. And instead of calculation of this function, I will just take the value from the Appendix A. And the temperature ratio is 165 approximately. So my T1 would be equal to 400 divided by 165. And now I will calculate how much. How much is the value? We have 400 divided by 165 is 242. 242 Kelvin. Do not forget, very important thing, that this is entropic relation. If you calculate temperature, you must use only Kelvin. You cannot use degrees centigrade, etc., because the ratio will be not correct. Just transform temperature you have to Kelvin and then perform all the calculations. So 242 Kelvin in point 1. Same thing I will do for point 2. I will just write in this absolutely same way as I did this formula. I will write that my temperature 2 would be equal to T0 divided by function of Mach number 2. Just now from Appendix A, I need to see what is the value of this function. So I will prepare here. T2 is 400 divided by, and my Mach 2 was 295. So the temperature ratio is 274. 274. Okay, and now I will calculate using this ratio. 146. 146 Kelvin. Quite cold, right? Becomes cold. But we are losing the potential energy of the flow, and we are transforming this potential energy to the kinetic energy of the flow. So Mach number rises and temperature, unfortunately, goes down. So it's quite cold, but very high velocity flow. So we have this temperature at point 2, and now I will make a transition from point 2 to point 3 through my shock wave, through my normal shock wave. I will go to Appendix B. The formula is quite long, so I will write from the new line. Is temperature ratio. Before is T2, and after the shock wave is T3. And it's same as the ratio of the enthalpies, H3 divided by H2, because if you remember, the enthalpy is Cp multiplied by T, and Cp for us is a constant. This formula to calculate the ratio of temperature, it consists of two parameters. We have to multiply 1 plus gamma plus 1 m squared minus 1. These formulas are received in the chapter 8, and they are precise formulas to calculate the flow properties or properties change on the shock wave, and they are analytical formulas. 2 plus gamma minus 1 multiplied by Mach number in squared divided by gamma plus 1 Mach number in squared. Okay, and to calculate this change, we use Mach number at a point before the shock wave. So in our case, it's Mach number 2. Mach number before the shock wave. I put subscript 2 in near every Mach number. This long formula, okay, it's a function 867 from the book. And instead of using this long formula, I will just use appendix B, the normal shock wave relation. Going back to appendix B, my M2 is 295, so I'm searching for 295 in the table inside appendix B, and this function would be equal to 262. So now I will just calculate T3 is equal to T2 multiplied by my 262. And I will calculate how much is. So I will use my 146 and multiply by 262. 382, or approximately 383. 383 Kelvin. And this is very interesting result. So we again, look, we have a high temperature, relatively high temperature at point 3, very close to the temperature inside the tank, inside the stagnation point. If we go here, we had 400 Kelvin before in the tank, not accelerated flow, and after flow accelerated, temperature decreased significantly because we had to use some part of potential energy to accelerate the flow, and after flow transits through the shock wave, Mach number significantly drops and same time temperature significantly rises. So this T3 is 383 Kelvin. Theoretically. Theoretically calculated, we assume that this estimation of the temperature is very close to the real temperature values. The Lambda-shock-wave we will study a bit later. Theoretically, you can see in the Anderson book that is a bit different. Let me remove this part. Removing too much. Okay. You will see in the Anderson book something like this is a straight line, right? A straight line. But in the real application, we have interaction of this shock wave with the boundary layer, and we are seeing like a lambda shape, some shock wave which is facing the boundary layer from one side and from another side. Yeah, I just try to design this shock wave more realistic than it is in the book. Just more realistic. There is no significant change in the computational part Just it would look similar to what you would receive, for example, in the numerical simulation once you are simulating your nozzle. So you will not be confused why you have in the book very straight shockwave, and when you are simulating you have lambda shape of the real shockwave. Just because of this, I try to be more realistic, to draw you the realistic flow distribution. Just this. In our calculation to estimate Mach 1, Mach 2, Mach 3, we did not need to know anything about temperature. We needed only to know pressure ratio. So you see that variation of Mach number is not strictly related with all thermodynamic properties. You can relate Mach number to just one thermodynamic property, for example, to pressure. You measure just pressure and you know the Mach number. And then temperature is an additional parameter which enters just to calculate the temperature distribution or velocity values, but not enters as an obligatory parameter. This is why inside the rocket motor we measure very few points of temperature. Usually we measure only the pressure distribution, and we know all Mach numbers, we know position of the shock wave even. And it gives a lot of opportunities for us. I mean, application of the gas dynamics theories to the real case, real flow. We do not see change of the gas properties, not gas constant or specific heat until we heat until 1500, for example, Kelvin. We do not see these changes, so we can definitely easily use this. But after we reach some values of temperature, we must make corrections in constants like gas constant, adiabatic constant, and others. Okay, you can use isentropic conditions actually everywhere when where there is no shock wave, where there is no shock wave or significant flow separation. In the case of high velocity, high temperature, these equations are still working. You just need to make corrections, which we probably have to discuss in the chapter of hypersonic flow. I think this would be more appropriate time to discuss. What you need to do is specify another parameters which we considered constant before, like gamma or Cp, Cv, R, and to make them parameters of temperature. Usually is a parameter of temperature. So it becomes more complex, the equation system. It's very common strategy, and it's working quite well.
Okay.
So, but we do not need to elaborate. You're welcome. We do not need to elaborate all the equations from the beginning. We just need to extend the equation system and do not consider anymore some constants as constants. We need to consider them as functions. There are several methods. Usually to calculate by hand is not possible anymore because it's not linear functions of temperature and not convenient to calculate by hand. Of course, if you use MATLAB or even Excel, you can calculate, but not by hand anymore because they are high order polynomial functions.